welcome everyone to the 5th Juice webinar in collaboration with Europlanet. Happy to see so many attendees today. We have 3 very interesting talks for you in store. This time the focus will be on Jupiter itself and what we hope to learn about its atmosphere, its structure, composition, building on what we already know. Let me introduce the 3 speakers. So Davide Grassi will be the first to talk. He will talk about Jupiter observations with the MAJIS instrument on board Juice. And he will also lift the veil on some first real data obtained last August during the Moon-Earth flyby of Juice. David is a senior researcher in planetary sciences at the National Institute for Astrophysics in Rome and a co-investigator on MAJIS. His primary focus of study of solar system atmospheres through infrared spectroscopy. He's been actively involved with Mars Express, Venus Express, and currently with Juice and also with Juno, and hopes in the future to join the journey to further planets, especially Uranus and maybe Neptune. Then the following 2 talks, we will hear about Jupiter as observed from Earth and how such observations will be able to support Juice in the future. First, we'll have Patrick Irwin, who will present brand new VLT MUSE Jupiter observations and what we have learned from the analysis of those. Pat is a professor of planetary physics at the University of Oxford. He was a co-investigator on Cassini, Sears instrument, and the Rosetta Virtus instruments. A team member of Galileo NIMS, that's where Pat and I met many years ago. And now he's also a co-investigator on Juice-MAJIS instrument. He's also the originator and lead developer of the famous Nemesis radiative transfer and retrieval code, and leads a program of ground-based and space-based spectroscopic observations for the interpretation of solar system planetary atmospheres. The final talk will be by Stephen Hill, and he will take us into his backyard in the US, which has a very nice telescope setup, and with which he observed Jupiter in a way that will make many professional and amateur astronomers jealous. Stephen is an amateur astronomer in Colorado, where there are a lot of sunny days and a lot of clear nights, about 300. So he says, and the light pollution in the city of Denver leads him to focus on the bright objects, such as the planets. Stephen holds a PhD in astrophysics, which he uses in his daytime job to support space weather observations. With this background, Stephen, he likes to push the boundaries of what can be done with backyard telescope equipment. And so these factors came together and leading him to investigate ammonia on Jupiter. And he will present these very, very nice results that he has. So that was for the introduction. Without further ado, David, I'll give the floor to you.
Okay, thank you. Thank you for your kind introduction, Martin. So today I will try to summarize briefly the science activities we plan to perform on the basis of the MAJIS data in the realm of the Jupiter science during the Juno mission. A few words about the mission itself. Also, the main objective of the mission is definitely related to the study of the icy moon of Jupiter, namely Ganymede. There will be, in any case, a long Jupiter tour that will last about 2 years before the Ganymede orbit insertion that will allow us to explore in details the other moons of the systems as the Jupiter planet itself. The Jupiter's observation will be mostly performed during the closest approach to the planet in periods of about plus minus 2 days around the closest approach. And this period is quite interesting for our purposes because it says that essentially we will be able to observe the same region of the planet repeatedly over few successive planetary rotation. And this implies, given the moderate inclination of the Jupiter of the Juice orbit, to explore the same region at different phase angles, since essentially the perigee of passage translates in very fast exploration of the phase angle space. The illumination condition varies considerably between the different perigee of passages. This is quite interesting for us in order to explore this very important parameter in terms of observation that could not be done from the ground observation, for example. But obviously this implies also quite a number of complications for the planning, since essentially we need to optimize very carefully each orbit in order to get the maximum of science return. The main obstacles in these very interesting pictures are represented by some mundane constraints that are represented by the data volume and a number of spacecraft operations that will need to be performed along with the very same data acquisitions. Coming now to our instrument, the MUSE and Jupiter Imaging Spectrometer. You can find a very nice introduction from our principal investigator, François Paulet, in this recent paper. And the main idea that we should keep in mind here is that we are dealing with slit spectrometers. Essentially, we are going to acquire the spectra in 400 spatially contiguous pixels that are aligned along a line. Essentially, this corresponds to the red line that is presented here above the disk of Jupiter. And then the images are created staking different spatial lines that are acquired sequentially in time, moving the slit all over the scenes. Essentially, this is an example of what we get. For example, we expect to achieve during the 12 perigee of passages. We present here 4 consecutive acquisitions. We call them cubes. Because the idea is that really for each pixel we are going to have a complete full spectrum. And the idea, you can see also in another way, is that we get a stack of monochromatic images, that we have a single images for each sampling point of our spectrum. Since we are dealing with the spectral capabilities of the instrument, we can go there in a bit more detail. We have 2 independent channels that in any case work together with the same spectral resolution, observing the same area and the same spatial resolution. We have a visible channel between 0.5 and 2.4 microns, and an infrared channel between 2.2 and 5.5. This could be usefully compared with this nice plot from Zromowski and Fry that present the level in the atmosphere at which we achieve a unit optical depth in a two-way cross of the atmosphere. And we understand that essentially with the MAJIS instrument, we can probe both the region that is dominated by the scattering of solar radiation, as well the one that is dominated by the thermal emission of the atmosphere. The main driver in shaping the Jupiter spectrum is given by the absorption of methane, but there is a number of other species, namely the molecular hydrogen collision-induced absorption and the ammonia, that will be a subject of also the discussion of next speakers, that could be effectively probed in those regions. So just to summarize the physics, the idea is that in the solar domain, we are mostly driven by the scattering provided by aerosol and clouds. Obviously, there is also a very important role by the Rayleigh scattering itself. But the idea is that the more opaque a given spectral region is, the higher the altitude responsible for those scattering is located. And given that we have a variability of opacity across the spectrum, this is a very effective way to provide a tomography of the cloud distribution. In the thermal domain, we are essentially dominated by the thermal emission of the deepest opacity sources. So why is that important? Essentially, to make the long story short, the MAJIS instrument can investigate the aerosol and the minor component in their spatial and temporal variabilities and composition, and this provides us very important constraint on dynamical models, on the thermochemical model, especially the exchange, the interplay between the minor component and the aerosol, and ultimately the energy exchange between the deeper level of the planet and the upper atmospheres. And this includes some contribution and studies we can perform on the basis of the auroral emission from the studies of the magnetosphere. So coming now to some specific example, we can take some inspiration from what has already been done. It is already in other studies by Zormowski and Fry. Essentially, from the visible and near infrared data, the most significant study we can perform are related to the vertical cloud distribution and the ammonia content. Those two aspects are really very much intertwined with each other, because ammonia is really expected to play a major role in the composition of the visible cloud of Jupiter. And on the basis of those data, we can provide important constraints on the aerosol properties. In those two examples, there have been studies on the South Tropical Zone and the South Equatorial Belt. In this field, MAJIS imaging capability will enable a systematic mapping of these properties, a spatial resolution typically in the order of 150 kilometers, and we can perform studies of the evolution of those parameters at different time scale, from few hours to few days, and from few weeks in the terms of different periods of passages. Another example that gives you a more specific idea comes from a limited example we were able to perform on the basis of the GRAM dataset on board of Juno. Unfortunately, we were very rarely in the condition to provide such an extensive mapping, but we plan to do something similarly and much more extended with the MAJIS data. What I want to stress, but that in any case, the improvement is not just quantitative, but also qualitative, because the retrieval of those parameters is indeed prone to a number of uncertainties, since we are dealing with a highly degenerate problem, as is summarized in these very nice studies here. And by the fact that the aerosol size, the composition, the vertical distribution, all can compensate each other to provide similar spectrum. And so as long as we are dealing with limited spectral range, we are in a condition when some of those uncertainties could not be completely solved. MAJIS can contribute really to reduce a lot of the degeneracies in the inverse problem, because we are going to acquire spectrum on an exceptionally wide spectral range. We are going to observe the same area at different phase angles and emission angle. It is a very powerful techniques that could be applied to constrain the scattering properties. And we are also comparing the same areas in the day and night time, something that could be done only from an orbiting platform. Similarly, if we are moving to the thermal region, we are exploiting the transparency windows of methane that is located around between 4.5 and 5 microns approximately. And we can probe the content of several minor species, especially mostly cloud-free regions, that, namely water vapor, ammonia at the lower level with respect to what could be done in the solar domain, and several disequilibrium species. And these are particularly important for the inference that we can make from the dynamics in the upper troposphere of Jupiter. Those are two examples of the fit that are well known to other colleagues that are attending here to the talk today. Once again, the imaging capability of Jupiter of MAJIS will enable a systematic mapping of those properties. And this is again a limited example that we had from the work we perform on the basis of the GRAM dataset. So the idea is that we are going to perform, as in the example provided here, a mapping, for example, of the water relative humidity and relate it with the morphology of the cloud that could be, for example, observed from the mapping in the infrared channel. Again, MAJIS will not just provide a quantitative difference, but also a qualitative one, because we will get a very much important extension of the spectral range to the region between 5 and 5.5 microns, that would allow us to probe the content of ammonia in the region between 1.5 and 3 bars. It was not feasible, for example, with the GRAM instrument. And this is particularly important because it's exactly the region where most of the condensation phenomena related to the gaseous ammonia are expected to occur. A final point that I would like to mention are the studies we can perform on the auroral emission. These are particularly interesting in a region where the methane is very much opaque. So essentially most of the solar photons are absorbed before being scattered. So the signal there is usually very low. And we can observe the weaker auroral emission that are generated by the impinging of the magnetospheric particles, and that generates H3 plus complex that essentially allow us to constrain the energy deposition from the magnetosphere to the upper atmosphere. And once again, we expect to substantially enhance the coverage of the data acquired by the GRAM instrument, covering also the expected atomic hydrogen emission at wavelength shorter than 2 microns. So this is just a summary of the capability that we expect to get with MAJIS. The idea is that what really makes this a unique opportunity is the blend of the large spectral range, the capability to explore in quite accurate and complete manner the phase angle space. And this really will enable us a number of new studies, especially when we have large data set as the one we expect to have, that could be exploited on statistical basis. Another point that I think it's fair to mention is the fact that we have a number of fellow travel that will be with us, the Genus camera, the ultraviolet spectrometers. There is an exquisite opportunity related to the short wavelength instrument, especially for the study of the upper atmosphere, and related to the connection with the impinging of particles from the upper atmospheres, also the data, the NA imager from the PEP instrument itself. I would like just to conclude in the last 30 seconds with showing you an example of the spectrum that the MAJIS instrument has already been capable to acquire during the Earth gravity assistance passage last year, observing the Earth atmosphere. And we were really pleasantly surprised among the team by the high quality of the spectral feature that we can observe. Here around 5 microns, you can see the very fine details that are related to the water vapors, and really is our hope that this quality of could be also replicated during the Jupiter studies. And that's all from my side. Thank you.
Thank you so much, Davide, for this very inspiring talk. Looking much forward to Juice getting to Jupiter. Pat, the floor is yours.
Right, let me just get myself going. Okay, can you see my first screen?
Perfect.
Excellent. Okay, so I'm talking about observations that we've made with the MUSE instrument at the Very Large Telescope in Chile, and the work we did to validate and verify the work that the next speaker is going to show about how Steve made observations in his backyard with a telescope and found all these amazing sort of maps of ammonia and cloud top heights. So I got involved in helping him write that paper, and in parallel with that, I did a study to try and figure out exactly what his method was doing and how it was producing such startlingly good results. So Okay, I can't see the right side on my screen because I've got the figures in. Never mind. So Juno was launched in 2011 and went into orbit around in 2016, and we started a program of observations at MUSE in support of Juno, because Juno goes in very low, periodic orbits. And I'm missing one of the diagrams. Okay.
Good here, Pat. It looks good here.
Okay, but it's in close in orbit, and so it can't. The measurement swaths are limited to very narrow tracks, and so there was a case to be made for looking at Jupiter from the Earth at around about the same time as these perijoves to get sort of in the global perspective. And the MUSE instrument at VLT is excellent for this because it's an imaging spectrometer covering 475 to 933 nanometers, and this is a false color image, a sort of true color image made from that. And this is one frame, this is one wavelength, and if I press this button, hopefully you'll see that we're going through all the different wavelengths from, and this is the wavelength in nanometers. And so as we go through these range of wavelengths, we can see higher or deeper in the atmosphere. And also we have the spectral dependence to tell us something about the nature of the chromophores, which give Jupiter's atmosphere its color. And we've had observations from MUSE covering almost every year from 2014 to 2023, and it represents a very valuable resource. Ah, that's the one I meant. I hadn't realized it was there. So this is the Juno orbit. I hadn't realized it was scheduled to be after the MUSE instrument. All right, never mind. Right. So we analyze our data with the mighty Nemesis, which is a very made-up acronym from the nonlinear optimal estimator for multivariate spectral analysis. And this was developed initially for looking at Cassini observations of Jupiter, Saturn, and Titan, but has since been extended to be applicable to any planet. And it handles thermal emission and multiple scattering. And the core retrieval code is based on optimal estimation. The main code itself was written in Fortran and has been our workhorse for the last 20 years. But the young folk don't like Fortran very much, and so the code has recently been rewritten into Python, which also has the advantage that we can now do nested sampling. And the Python version, which is called Arch Nemesis, is now available. So we took the observations with VLT and processed them with Nemesis, and we used that to retrieve maps of cloud opacity and ammonia, and that appeared in a couple of papers which I've listed there. These are accurate retrievals. We take full account of everything, but the multiple scattering needed to achieve to fit the spectra is very, very slow. And so the retrievals are limited to latitudinal averages or to a few interesting regions. However, we did find high ammonia in the North Equatorial Belt and low ammonia in the equatorial zone, which are consistent with other observations. And I had a graduate student working on this, and we're working on new methods. And while we're doing this, Stephen Hill came along. With his using an old simple method and a backyard telescope, and with just a few filters, he was able to achieve almost exactly the same results as we did, which came as a bit of a shock. And so this talk and the paper we wrote with this is how on earth did he do it? So this is a comparison of the spectra of the Sun, Jupiter, and Saturn. And on the right, I've made what you'd see if you were looking at through a spectrometer. And for Jupiter and Saturn, you can see that there are absorption bands that you can see with visible wavelengths of methane at 619 nanometers and a faint band of ammonia at 647 nanometers. And these wavelengths have previously been used to map the abundance of ammonia and cloud top pressure in the atmosphere. But with more recent measurements and bigger models like Nemesis, the attention moved to the near infrared, where there's less problem with radio scattering. However, obviously, the visible wavelength range is very handy for people who are working as amateurs, and so it turned out that you can actually use these bands to do some really good science. So this is showing on the top we've got a reflectivity spectrum of Jupiter, with the pink region is the methane band sort of filled in so you can see it, and the blue region is the ammonia band filled in. And on top of that are the three filters that Steve used, and he'll tell you about that in his talk coming up, that he used to basically measure the depth of the strength of the absorption in these two bands. On the bottom two plots, I show the absorption strengths of methane and ammonia, so you can see what feature relates to what. So if you take ratios of the reflectivities in these different filters, you can get a mean transmission of methane and a mean transmission of ammonia, and then you can convert that to optical depth by taking the logs. More usually, we look at the strengths of these things in terms of this thing called the equivalent width, which is just the if you take 1 minus the transmission and integrate it, you get a number which is the width in nanometers a uniformly absorbing band which has the same overall depth. So I'm afraid I've got to show you some maths. If you assume that both gases are well mixed above the cloud tops, then if you know the mole fraction of methane, which we do from the Galileo entry probe, then you can figure out the mole fraction of ammonia by taking a ratio of those optical depths and divided by the absorption strengths, which we know from lab measurements and other measurements. Furthermore, if we assume that the clouds are very sharply defined tops, then from the strength of the methane absorption band, we can figure out the cloud top pressure, because basically the deeper the cloud is, the more methane is going to absorb, and so the deeper the absorption will be. And in that expression, m is the molecular weight, gravity is g, you've got Avogadro number, and there's also the air mass factor, eta, which is one of the cosines of the solar zenith angle and the viewing emission angle, and that's obviously equal to 2 for nadir viewing. So we took Steve's technique and we applied it to our measured MUSE spectra. So obviously we can take our spectra and integrate over the same filters that Steve used, and then compare our results with the full Nemesis retrievals. Furthermore, as we have complete spectra, we also developed a slightly modified version of this technique, which better fits the continuum. But the results are pretty similar with Steve's for Jupiter. They're slightly different for Saturn, but that's another talk for another day. And this is what happens when we apply that technique to our data. So on the left are the reflectivities measured at 619 and 647 nanometers. The second column is the computed transmissions of methane and ammonia. The third column is the optical depths. And the fourth column is the cloud top pressure and the ammonia. And you can see that we can, from the scale bars, because we've assumed an air mass factor of 2 rather than 4, and this gives us an air mass factor, gives us a cloud top pressure of 2 to 3 bars, which is a bit surprising, given that common knowledge is that clouds are made of ammonia. Putting the pressure aside, if you look at the ammonia map, we can see some fantastic details here. We can see that there's high ammonia just north of the equatorial zone, and there's low ammonia to the north of that, and there's also low ammonia of the Great Red Spot here. But going back to the pressure, I mean, why are we getting such a high pressure? Equilibrium cloud condensation models predict that we should see 3 cloud layers. We should see an ammonia cloud at 0.7 bar, and this is basically where the condensation curves meet the temperature curve. We expect to see ammonia ice at 0.7 bar. We expect to see ammonium hydrosulfide at 2 bars or so, and water ice at sort of 5 bars or so. That's what we expect. What the Galileo entry probe saw when it landed, but it sort of dropped through the atmosphere in '95, was rather different, where it's found a sort of small clouds that may be the upper half of the NH3 ice layer and the NH4SH solid layer. But was this just because the probe fell into an anomalous 5 micron hotspot, or is this cloud structure actually more representative of the global cloud structure? So if we assume the air mass factor of 2, we find the cloud tops are formed at 2 to 3 bars. But as I say, the simple model would suggest that we should be finding the clouds at 0.7 bars. So what we did here was we calculated 2-way transmission spectra in a standard aerosol-free atmosphere, including radio opacity, and that's on the bottom. And as you can see, as you go to deeper and deeper pressures, the absorption strengths of the different bands, of the methane band at 619 and the ammonia band at 647, they increase. And if you take those spectra and work out the equivalent widths, then you can plot how the equivalent width grows with pressure, and that's shown on the top left corner here, where we have the blue one is for ammonia and the pink one is for methane. And the vertical dashed lines there are the measured equivalent widths that we find from the cloud top spectra. And you can see that where the blue curve meets, that's around about 3 bars, and where the pink curves meet, that's about 3 bars. And so this does seem to suggest that the cloud tops we're seeing are at 2 to 3 bars. So why? Fortunately, because we've got an integral field unit spectrometer, we can use limb darkening, and we can use that to test this result. So from the MUSE cube, we took the spectra along the equator, sort of 1 degree either side, and we measured the equivalent widths of the methane and ammonia bands at all points on those, and then plotted those widths as a function of the air mass. And if the Jupiter edge transfer is as we've assumed it to be with the reflecting layer model, as being a very thin cloud with a sharp top, and light coming in from the sun and then going away to the observer. If that is our model, then the air mass obviously will increase as the solar zenith angle or viewing zenith angle increases. And so you'd expect the equivalent width or the depth of the absorption bands to increase with that air mass factor in a sort of linear way, which is shown on the right-hand side here. And that shows how the W increases with the air mass factor. So that's what we expect. If our model is correct, that's what we expect. This is what we saw. We actually find that the equivalent width actually decreases with the air mass factor. And hence this idea of the clouds having a sharply defined cloud top is not true. In fact, the aerosols are vertically extended, and hence, when you're going at a higher zenith angle, you can't see down as far. The other thing we noticed is that the ammonia equivalent width drops faster than the methane one. On the left-hand plot here, the light blue curve, the light blue dots are the ammonia equivalent width scaled roughly just to match the methane equivalent widths at the air mass factor of 2. And you can see they drop away much faster with air mass than methane. And on the right, I've plotted the ratio of the equivalent width of methane and ammonia. And you can see that they follow this line. So you can then use that curve of growth and compare it with our rate of transfer models. And if you were to put the cloud top at sort of 1 bar, which is the purple line here, you can see that we'd expect that the ratio to be much sharper, because we know that ammonia condenses. And so if you were at the 1 bar level, going to higher zenith angle, the amount of ammonia above there decreases rapidly with pressure. And so you'd expect that ratio to drop away very rapidly. If the cloud were deeper, then you expect a slower variation of the gradient with air mass. And so looking at this with this rough analysis, you can see that even the limb darkening suggests that the main reflecting level is around about the 3 bar level. Okay, so the clouds need to be deeper than the expected condensation level, and this is actually consistent with a number of previous studies, but it's particularly compelling as the evidence is really simple. Sometimes these results are sort of hidden away in a retrieval black box, and it's really hard to appreciate or validate whether the results are true. Here, it's very hard to argue against the main reflecting layer being deeper than the expected ammonia cloud condensation level. And hence it would appear that ammonia must be photolysed faster than it can be convected upwards, we think. And we think the main cloud is probably a mixture of ammonium hydrosulfide and photochemical haze. But what about the gaseous ammonia? So the method seems to be finding the deep abundance, which has previously only been achievable with radio and microwave observations, such as VLA and Juno MWR. So how can this be? So this is a comparison of nemesis retrievals of ammonia, which are the black line with the grey error curve, and 2 applications of the band depth method, one using the direct Steve's method Hill, and one using the slightly revised version that we made, which is slightly more precise. But you can see they give roughly the same results. You can see that the latitudinal variation is almost identical, but we can see that the band depth methods are too small by a factor of 1.5. And we realized that this was because the band depth method assumes that both ammonia and methane are well mixed. But in fact, we know that that ammonia condenses, and so its volume mixing ratio drops with height. And if you take that into account, we call it the alpha correction, then you get a much better correspondence here between the formal nemesis retrievals and the band depth methods. And so that means, because we've validated against formal retrievals as a function of latitude, that means that the spatial variations that Steve's getting with his method, and which we've reproduced here with VLT, look much more plausible and seem to be telling us something very interesting about how ammonia and cloud top pressure vary across discrete features across Jupiter's disk. And as is ongoing with that, I expect Stephen will talk to you about that in his talk. Finally, just comparing to see how good this is, on the left is ammonia derived from the VLT MUSE data using the band depth method. And on the right is ammonia as retrieved from the very large array at 8 to 10 gigahertz. And I've color coded it in the same way, such that black is low amounts of methane and white is high. And you can see that we get very similar latitudinal variations and a sort of similar variation over the Great Red Spot. There's our Great Red Spot, which is bright here and dark to the north, and here's their great red spot, which is sort of bright and dark to the north. Similarly, it also corresponds well to microwave radiometer results from Juno. And so here I'm comparing our retrievals with Nemesis and with the Bandit method with variations of ammonia with latitude derived from MWR. And again, we get a very good correspondence in the shape, not quite so good correspondence in the overall factor, and that discrepancy is still being investigated. So in conclusion, with a very large telescope within the reach of amateur observers and with just 3 or 4 narrow filters, it turns out you can map the cloud top pressures and abundance of ammonia at about 3 bars in Jupiter's atmosphere, which is amazing. We also showed in our paper that I referenced there that you can apply the same method to Saturn. And the method produces maps of Jovian ammonia that aren't so very different from multi-million pound instruments on Juno, on VLA, and allows for a detailed feature analysis of both the VLT MUSE observations and from biometers. And our cloud tops, as we find, are not at the ammonium cloud concentration, but some are deeper, and work is ongoing to figure out exactly what's going on there. Okay, how's that? I'll stop sharing.
Thank you so much, Patrick, for this very, very nice talk indeed. That was great. So let's go to Steve. Oh, you're muted, Steve. You are still muted.
Okay. One
yes,
moment.
Now we can hear you. And we do see a little bit of these bars. I think you.
How are we now?
We still have a little like bar. Yes, in the bottom of the image of the screen. Maybe it's related to.
One moment.
Yeah.
Just one moment here.
Sure. No problem. If you prefer, Callum could share the slides as well.
Let me know what you prefer, Steve. Yeah, keep going.
That's there fine. We go.
Okay.
That should be
perfect.
Good.
Perfect. Yes, perfect. Thank you. Perfect.
All right. Good afternoon, everyone. Thank you for your interest in these amazing talks. I do want to especially acknowledge Pat and others in the professional community that have really been of great support to me in this inquiry, as I have just learned a ton in an area that is not my core subject matter expertise. And in particular, as you saw from the previous talk, Pat has really completely delved into the physical meaning and the implications of the band average method in a way that I simply could not. And that's really terrific, because that's really validated the method and sort of shown that it actually is quite useful. So let's see, slide advance. There we go. Okay, so my equipment is, it's not grandiose, but it's not entry-level amateur equipment. It's a Celestron 11 on a automated computer mount. I've got a small planetary camera that's really based on webcam technology. I use a 7-position filter wheel. All of these things, the accessories here, as opposed to the actual telescope, are in the hundreds of dollars or hundreds of euro range. They're not thousands or tens of thousands of dollars. Where the key thing comes in for this band average method is that there are custom filters required. And those custom filters are the 620 nanometer, 632, and 647 nanometer bands for the methane, continuum, and ammonia bands. And here I give the part numbers and approximate costs. I ordered mine from Edmund Optics. They are 10 nanometer bandpass filters, and they actually mount fairly nicely into standard filter cell mounts for amateur grade equipment. And then finally, I use SharpCap capture and automation software so that I can take lots of video data of Jupiter without having to sit out in the cold and the dark all night. For data reduction, I use mostly free software, Registax, to stack the video data into images and to select the highest quality of the video frames. MaximDL for some image processing and white balance for the different bands. And then I use WinJuPose for image navigation and mapping. And on the right-hand side here, it's an example array of processed images. On the top, you have methane. So there's a radiance image on the left, a methane transmission image in the center, and then that's converted to opacity on the right-hand side. The second row is the same thing except for ammonia. So you see some similarity here to the MUSE images that Pat showed, except with poorer resolution. And then on the bottom row, I've got on the left the effective cloud top, and I'll use cloud top pressure very casually here, acknowledging that we've got a extended cloud of some depth, and we're not talking about a sharp edge top. A context image, and I typically use broadband IR for the red channel here. It gives me a little bit more spatial resolution. And then you've got the ammonia mole fraction on the right-hand side. So this gives an example of what a single observation looks like from a set of videos in the different channels. Now, what I can do is I use Python extensively for the analysis and for post-processing and data reduction afterwards. And the first thing that I really do is I create maps, and I create them in a FITS format, and then of course you can plot them in any fashion you want. Here I have stitched basically 24 individual observations into these maps, one for ammonia on the top, cloud height in the middle, and the context image on the bottom. Each longitude is really represented by 5 to 7 different zenith angles. And that is really nice because that gives you both redundancy and statistics in terms of measurements at that location, and it gives you the opportunity to study limb effects there. And for creating the maps, though, I've used an empirically determined limb correction. So you can see a lot of features here. You can see the depleted ammonia in the North Equatorial Belt. I've color-coded these, so it's kind of the color codes here are kind of what's used in the terrestrial environmental sciences. So for ammonia, I've used like a waterish color table. So where there's more ammonia, it's bluer. Where there's less ammonia, it is a drier brown or white color. And then for the cloud top pressure, where it's white, those are very high clouds. Where you're seeing deep into the atmosphere, that's a darker blue. So you can go on beyond just looking at these global maps, and my approach has been to use a region of interest approach just to focus in on specific features and see what could be learned about them, really from an observational, empirical sort of perspective. So if we look first here over at the SEB outbreak that occurred initially in November of 2024, you can see, I'm going to just use a pointer here for a sec. You can see that this is the main longitude of the outbreak. There is a disturbance to the east, and that's in the context image. In the cloud height, you can see that these are higher cloud areas, but they're not super dramatically higher than, for example, the south tropical zone here. You can see that there may be some effects seen in the ammonia images, but they may not be exactly what you expect. It looks like the ammonia is actually a little bit drier over the main cloud top here of the convective cell. And that's probably because you're seeing above the area where the ammonia is drawn out, whether it's through condensation or combination into other clouds or photochemical reactions. So you're not actually seeing an enhanced ammonia there, but a depleted because you're looking higher up. And Next, we look at a hotspot and plume. So if you look at the context image, and unfortunately it's rather blurry over here, really you've got a hotspot sitting here above where you've got the maximum ammonia concentration. So a little bit to the north and west of where the peak ammonia is. And that's a kind of interesting finding that has been seen before, both using this method and prior methods. So exactly what's happening with ammonia there is definitely a ripe area for further investigation. And then if we look at the Great Red Spot, we can see a depletion in ammonia there. We can see the heightened cloud, and you can see how that lays out all on a image of the red spot. So we can delve deeper into that, as I implied by these small boxes, which are the specific regions of interest. But first, I do want to point out that besides computing an average of several images here at different zenith angles, we also compute the standard deviation. So that really gives us an idea as to whether we have any outliers or any real noise problems. And those do occur, and specific observations have to be dropped for that. You can see that this is a pretty darn clean observation. The variation between the 5 or so images that were composited here, the fractional standard deviation is very low. It's around 10% for the ammonia on a pixel-wise basis, and in the neighborhood of 5% for the cloud retrieval. So that's kind of cool. And within each of these little boxes, we do compute statistics. So we get means, standard deviations, and we can also look at these over time or over the zenith angle. So the first thing we look at here is the time variation of the different samples here. And you can see, for example, the most depleted ammonia is right in the center of the Great Red Spot. That's that sort of dark blue box. I'm not going to go into each of these lines because obviously it's kind of an eye chart here. And one of the important points to make here is that these sort of larger jumps, this covers a period, by the way, in 2022 from August to October. The kind of larger jumps may be due to physical variation, or they may be due to systematic errors that have to do with seeing conditions or the calibration of the telescope, flat fielding artifacts. That there are some things that could be causing these problems that are not necessarily physical. So that really requires some further investigation before we assume that those are physical results. Now on the next page, we, rather than looking at the time variation, we look at the overall average. So first we've plotted all of the samples here from these different regions of interest, and you can see a general trend here that's very interesting. From the upper left, the high pressure, low pressure, low ammonia, to higher pressure, higher ammonia, which is as you'd expect. The deeper you're seeing into the atmosphere for a specific feature, you expect to be seeing into higher levels of ammonia. If I average each of these features, so we average the core of the Great Red Spot over the 5 or so observations that were made, we do the hook, which is over to the west here, the wake, etc. What you find is you still see that trend from low pressure, low ammonia to high pressure, higher ammonia, but you also see some points that may be outliers. I mean, the error bars are still pretty large here, and it certainly requires a lot more investigation to determine whether this is a real effect. But it is interesting that the convective wake and the south tropical zone seem to have higher than, I put expected in quotes, ammonia mole fraction for their pressure level. That is, they don't fall on sort of this empirical trend line. So again, just hooks for ideas for investigations. So jumping now to a more global level of investigation and longer term change, we're looking at meridional profiles of cloud top pressure on the left and ammonia abundance on the right. And the black lines that are a little bit thinner are data from 2022 from both my backyard and from VLT MUSE. And then the blue curve is from 2023 and the orange curve is from 2024. And the thing that is really evident here is there's a kind of dramatic change in the equatorial zone in terms of the cloud depth. You can see that pressure increasing significantly from 2023 to 2024 as the higher clouds clear and we're seeing deeper into the atmosphere. A similar thing happens at the northern edge of the North Equatorial Belt and the North Tropical Zone, where you've got a NEB expansion ongoing during that period of time. If you look at the ammonia result on the right, you can also see that there appears to be some change in terms of an increase in the equatorial zone, and it's unclear with the North Equatorial Belt, but you also notice that there's an offset kind of globally in ammonia. That may be a year-over-year calibration difference, and that requires investigation as well. But to get a look, if we set aside for a moment the absolute offset in this, and we want to get a little bit more look at the changes, we can go ahead and look at the differences from one year to another. So now, instead of plotting the actual cloud top pressure and the ammonia, we're plotting the change, the year-over-year change. So the blue curve represents the change from 2022 to 2023, and the orange curve represents the change from 2023 to 2024. So you can see just really dramatically here the effective cloud top pressure increase, the clearing in the equatorial zone disturbance activity that went on, as well as the ammonia increase that happened there. And similarly, you can see that decrease in cloud height for the NEB expansion. And you can also see, relatively speaking, an increase in ammonia, mostly quite kind of at the border between the NEB and the North Tropical Zone. And again, that assumes that this is sort of a secular, a systematic error, but we can see that, at least relatively speaking, we've got increases in these regions. And so again, this offset needs to be investigated. And then if we go and plot this instead on a two-dimensional plot that shows cloud top pressure on the left and ammonia mole fraction on the horizontal, similar to the way I had these plotted earlier for the regions of interest, what you find is you can see the NEB expansion, the clearing of the deeper clouds is represented by these sort of two arrows, the brown and the lavender, with a significant increase in cloud top pressure, that's the clearing, and a decrease in ammonia mole fraction. And that's on an absolute scale. And then for the EZ disturbance with the green and red arrows, you can see the increase in cloud pressure, the clearing. And then we have the South Tropical Zone and South Equatorial Belt, both showing a decrease in ammonia, but the South Tropical Zone showed higher clouds. So this might be an effect, oops, let me go back a second here. This might be an effect of that offset of ammonia. We may actually be seeing the NEB and the EZ disturbance showing both a decrease, an increase in cloud pressure, and an increase in ammonia, rather than sort of not so much change. And again, that's possibly that offset. And then finally, I wanted to talk about a comparison with 5-micron data from IRTF, and that's courtesy of Glenn Orton and Tom Elmery. So I plotted first here the ammonia mole fraction from my observations. Here is the 5-micron measurement from IRTF for the same date, only a few hours difference. And then here is the cloud pressure from the optical observation, from my optical observation. This is in September of 2022. And so in this case, we know that the 5-micron emission is brighter in clearer areas. So, you know, the bright orange that you're seeing in that middle panel is the deeper areas of cloud. In the optical cloud map, the dark areas are the ones that are clearer according to the color scheme I chose. But what if we go ahead and change the color table and we change it to sort of match deeper clouds are in a brighter orange? Then we start to see a lot of at least qualitative similarities between the 5-micron data and the optical cloud top data. And that's not unexpected at sort of a high level of thought. The details as to how that happens is, again, a sort of curious thing here. So just when we look at the 5 micron data, what are we seeing? Well, first of all, we look at the optical data. What we're seeing is basically reflected sunlight, and we are seeing that sort of darkness, or the deeper clouds are due to higher absorption, the longer air mass path to a deeper reflecting area. And if we're looking at the 5 micron emission, we're looking at deep emission that's passing through the aerosols. And the question really gets to be, are the aerosols that are responsible for the increased absorption in the optical the same aerosols that are causing decreased emission in the 5 micron band? And just to dig a little bit deeper into this, I plotted a scatter plot again on the upper right. We've got basically the 5 micron radiance with the contours of the optical cloud height overlaid, and you can again see the very good qualitative match there. But what you also see is if you plot the 5 micron radiance on a log scale, you get a very nice pattern in terms of the relationship to the optical cloud top pressure. So that's interesting. What does it tell us physically? Well, I'll turn that over to Pat and Glenn and others for that. But I think it's an interesting relationship. The ammonia relationship on the bottom is, of course, more complicated, and I can't really say what that means. It's not got a clear pattern to it. Oh, and then finally, obviously, amateurs often look at the 889 nanometer strong methane band, and that's really giving us the highest hazes and clouds, and I don't believe is going to have a very close relationship or impact on the kinds of measurements that this band average in the weaker optical bands of ammonia and methane are showing us. So to wrap up, the band average method provides a new view of clouds and ammonia, and Pat's provided, just great information on quantitatively what that means and what some of the implications are. The method is affordable, accessible, and effective. It provides a rich data set, especially when combined with other spectral domains and targeted observations. Automation and amateur participation could greatly expand coverage, and I think this is a really terrific opportunity for pro-am collaboration. And you can see just in a couple of years what automation has done for my own observations here. I am well over 350 observations during this observing season, and looking forward to a few more before the end of that. So that's it, and thank you very much for listening.
Thank you so much, Steve, Pat, and Davide for your really, really nice presentations. Let's see, there are a few questions. I saw one hand raised already quite in the beginning. I'm not sure whether the raised hand is still there. If you want to speak, then please do so. Otherwise, we have 2 questions in the question box. And so I'll just go ahead. So the first question is by Ben Atwood. It's for Patrick. Do you think that the methods you have outlined could also reliably be applied to Uranus and Neptune's atmospheres using amateur equipment?
Well, I mean, Uranus and Neptune are much smaller, much harder to get a number of pixels across the disk. And also with Uranus and Neptune, the only absorbing gas you can see in the visible is methane. So I guess you could use it to so you can't do this direct thing because this method is a band depth. It's ratioing ammonia to methane, whereas on Neptune and Uranus you just have methane. But obviously, if you look at different wavelengths where you have more or less absorption of methane, you can probe higher or lower in the atmosphere, and so you can map out the polar hood and discrete clouds, for example. If you've got really good resolution on a really good night with really good seeing, then you can do that.
All right. Thank you, Pat. I hope that answers your questions, Ben. The next question is by Mark Elowitz. Since there is ammonia present in Jupiter's atmosphere, has hydrazine N2H4 ever been observationally detected in the stratosphere? where it is cooler and hydrogen could be more stable. Will juice be able to detect hydrogen if it is present? So I guess it's a question for Pat and Davide.
Okay, so hydrazine is thought to be what the ammonia fertilizes to, and I'm not aware personally that there is direct evidence of its existence in the atmosphere, but I'm very happy to stand corrected on that. Davide, do you know?
I'm not aware of any positive detection of hydrazine neither, but I remember we performed some test in trying to fit the shape of the 2.3 micron radius maximum in the GRAM data. And as far as I can remember right now, the conclusion was that hydrazine should have quite clear spectral features in the range that in any case going to be covered by also by the MAJIS instrument. So obviously we should understand of what amount we are talking about, but the spectral range is there and for the detection of hydrazine. But from what I remember, our search for that on the GRAM data was unsuccessful up to now. So I don't see that from the spectroscopic data there is evidence right now from of this compound.
Okay, thank you so much. I hope, Mark, that answers your question. Then Glenn has a question for everyone. What sort of Earth-based observations would you like to see to support the JUICE mission, if any? This is both during the active mission and prior to JUICE's arrival. For everyone, I guess, to speak up.
Well, as much as possible, obviously. I mean, you know, just all data is good data. Yeah, I mean, Davide, I mean, you're more aware of the mapping patterns of MAJIS and things. I mean, what would be a good backup observation to be made?
I think that the most important things for that would be the time continuity that this kind of observation could provide, because in any case, I briefly mentioned the issue related to the data volume that in any case we must cope with. And so I really think that in the outside the peerage of passages, we can realistically perform some regular observation of the Jupiter disk with a period of at maximum 3 days. I think it's going to be very important to have a quite continuous monitoring of the Jupiter atmosphere also outside those periods that could be covered by the instrument. So in my view, the time coverage is the most important one by far. Moreover, probably we should also keep in mind that unfortunately the instrument that are on board of JUICE stops at 5.5 microns. So whatever kind of telescopic observation that go to longer wavelengths would be of the greatest importance for us. Unfortunately, we were not able to put spectrometers that goes down to the very low thermal wavelengths around 10, 15 microns there. So this would be something that there were definitely an area of simultaneous observation that is going to be extremely important to provide the further context of what we are going to observe with the payload of the JUICE mission.
Yeah. Yeah. Anybody else wants to comment on that? Glenn says thanks. Okay, is there any other questions from the attendees at this point? Then I have a small question. So Steve, you have sort of developed this method now, you applied it, and we've seen the magnificent results. How are there other amateurs doing the same thing at the moment that you're aware of? Or how could we coordinate this or make other people aware? And I think maybe I think is Augustin Sanchez Lavega. He was online. He's also, or is he not coordinating also Pro-Am for Jupiter, Pro-Am activities for Jupiter? So just wanted to throw that in the.
Yeah, I've given this a fair amount of thought. I think this is, you know, it's an awfully niche sort of study for amateurs, but there are high-end amateurs who really do terrific studies of Jupiter and might be interested, but it's not a really large group. If we want to sort of expand that, I've tried to figure out whether or not there needs to be some more formal organization rather than simply promotion via webinars, etc. I do know of a couple people who have expressed interest in doing this method to provide more coverage of Jupiter, but I've not really heard of any progress at this point. But if there were to be some, you know, slightly more organized citizen science approach with a clearinghouse for this kind of data, obviously, like the WinJupose effort, just does fabulous in terms of visible light observations of Jupiter and tracking features and early alerts and all of that. Something that would be a little bit more organized to sort of bring this into the fold of more normal, so to speak, citizen science on Jupiter.
Excellent. I think we should take this along and in the coming time try to organize that more systematically, also in coordination with the Juice project and with MAJIS team, and could be really good. Yeah. Okay. Any other questions or comments? I just have one quick one. David, is there going to be a paper on the Earth flyby from the data?
I think I'm not personally working on that. I am quite sure that there is a number of colleagues that are actively working on those kind of analysis. So I'm quite confident to say yes, there's going to be some extensively reports on that, and almost sure in terms of publication on that. So there is a couple of colleagues that at least are working very hard on this, and it's not just for the task of validating the instrument itself, but also to perform some genuine science on this. And we have, again, by the hands of Patrick, a very good precedent case from the analysis of the flyby of the data from Rosetta mission that demonstrated to be extremely interesting, not just for the instrument itself, but for the science. So it's always very nice when we have a new instrument working still on the good old planet, and very interesting things come out. So yes, I think quite confident that soon we will see some publication on that.
Excellent. Okay. Good. Maybe one final question. That will be it. If there's no other ones. So Pat and Steve, what's coming up? Is new VLT MUSE is continuing to observe every year, and will you continue to collaborate on this and get more accurate data? What's the plan?
Well, we're continuing to put in proposals for VLT MUSE, but they're not, but they're no longer not having such success getting them accepted. So we'll keep on proposing. I mean, the measurements don't take very long because MUSE is massive, and so just one of those frames takes about 2 seconds. Yeah, it's amazing. I mean, there's all sorts of time taken to slew the telescope and set it up, but the actual exposures are very quick. We will keep trying on that, and yes, I mean, I hope to collaborate more with Steve in the future. I mean, we've got there's lots we can work on, and I'm certainly taking the what we've got from this result and seeing how it relates to what we see at longer wavelengths through Galileo. I'm currently reanalyzing Galileo NIMS spectra, Martin, the RT spectra, and I'm going to reanalyze Cassini VIMS as well to try and see if I can find a solution that matches all wavelengths. But that's work in progress.
Excellent. Okay.
Yep, and definitely looking forward to more collaborations with Pat and other professionals. I am just enjoying how much I'm learning and trying to find ways to contribute.
Excellent. And I'm sure that will happen. There's a final, François Poulet, the PI of MAJIS, is online. He writes, yes, I confirm that a few papers are being planned. So that's good. We will look on the lookout for that. All right. Okay. Thank you so much, everyone. I think we'll close it here. We had a very nice session. So thank you very much for your contribution, for all the attendees, and see you next time.